Imagine for a moment that you are standing on a quiet railway platform at sunset. A train rushes past you at great speed, and from one of its windows a passenger throws a ball forward. To you, the observer on the platform, the ball appears to move faster than it would if the train were standing still. This is common sense. If the train moves at 50 kilometers per hour and the ball is thrown forward at 10 kilometers per hour relative to the train, then you would naturally say the ball is moving at 60 kilometers per hour relative to you. For centuries, this was how the world was understood. Motion was relative, yes, but speeds added together in a simple and predictable way. This was the world of Isaac Newton, where space was an infinite stage and time ticked forward like a perfect universal clock. Everything seemed orderly, logical, and intuitive, but light refused to obey this comfortable logic. In the 19th century, physicists began studying light more carefully. They discovered that light was not a stream of particles in the old sense, but a kind of wave, an electromagnetic wave, described beautifully by James Clerk Maxwell's equations. These equations predicted something astonishing. Light always travels at the same speed in a vacuum, a very precise value we now call c, approximately 300,000 kilometers per second. At first, this seemed harmless, but then came a troubling question: relative to what? You see, every wave known at the time needed a medium. Water waves moved through water, sound waves moved through air, so scientists assumed light must travel through some invisible substance filling the universe. They called it the luminiferous ether. This ether was imagined as a kind of cosmic ocean, perfectly still, through which light waves rippled. If the Earth moved through this ether, as it surely must, since it orbits the sun, then the speed of light should appear different depending on the direction you measured it. Just as a swimmer moves differently with or against a current, light should seem faster or slower depending on the Earth's motion through this ether. So in 1887, two scientists, Michelson and Morley, performed a remarkably precise experiment. They measured the speed of light in different directions, expecting to find a small difference caused by Earth's motion through the ether. But they found nothing. No matter how they measured it, the speed of light remained the same. There was no ether wind, no preferred direction, no difference at all. This result was deeply unsettling. It meant one of two things: either the experiment was flawed or the entire foundation of classical physics was incomplete. For years, physicists struggled with this paradox. They proposed strange ideas. Perhaps objects shrank in the direction of motion, or clocks slowed down, but only in very specific ways. These were clever mathematical tricks, but they lacked a deeper understanding. Then came a young patent clerk in Bern who asked a simple question: what if the speed of light really is constant for everyone? Imagine, he thought, that you are chasing a beam of light. Suppose you run at nearly the speed of light itself. According to Newtonian logic, you should see the light wave moving slowly ahead of you, perhaps even frozen in space if you matched its speed. But Maxwell's equations did not allow for such a thing. A stationary light wave was impossible. This contradiction troubled him deeply. It was like a splinter in the mind that could not be ignored. So he proposed something radical. The speed of light is not just constant relative to some ether, it is constant for all observers, no matter how fast they are moving. This idea required a sacrifice. If the speed of light never changes, then something else must, and that something was the very fabric of reality, space and time. If two observers move relative to each other, they will not agree on distances or durations. Their rulers will measure different lengths, and their clocks will tick at different rates, yet both will measure the same speed of light. In other words, space and time are not absolute. They stretch and compress to preserve the constancy of light. This was the first pillar of the special theory of relativity, published in 1905. Its central postulate was simple: the speed of light in a vacuum is the same for all observers, regardless of their motion. The speed of light in a vacuum is the same for all observers, regardless of their motion. From this single idea flowed a cascade of strange and beautiful consequences: time dilation, length contraction, and eventually the realization that mass and energy are interchangeable. But at its heart, the idea is almost poetic. Light is the universe's ultimate messenger, and it travels with a speed that is not negotiable. No matter how fast you run, no matter how powerful your engines, light will always outrun you at the same unchanging pace. It is as if the universe has set a cosmic speed limit not merely as a rule of motion, but as a fundamental feature of reality itself. And so, what began as a puzzling experimental result became a profound insight. The laws of nature are written not in the language of absolute space and time, but in the deeper, more subtle language of space-time, where the speed of light stands as a universal constant, a silent guardian of the structure of the cosmos. For most of human history, space and time were treated as two entirely different things. Space was the grand stage, vast, silent, and unchanging, where all events took place. Time, meanwhile, was the steady ticking of a cosmic clock, the same everywhere in the universe, advancing second by second without hesitation or variation. This was the view given to us by Isaac Newton. In his universe, space was absolute, time was absolute, they existed independently of everything else. Whether you were standing still on Earth, riding a galloping horse, or sailing across the ocean, time passed for you exactly the same as it did for anyone else. Every clock in the universe, if built perfectly, would tick in perfect agreement. It was a comforting idea. It made the universe feel orderly and predictable. But as the 19th century gave way to the 20th, small cracks began to appear in this neat picture. Experiments involving light, electricity, and magnetism hinted that something was not quite right, and the most troubling clue came from the constancy of the speed of light. If the speed of light is the same for everyone, no matter how fast they move, then something very strange must happen to space and time, because speed is simply distance divided by time. If the speed remains constant but observers are moving relative to each other, then their measurements of distance and time must change. This realization was the beginning of a profound transformation in our understanding of reality. Let us imagine a simple thought experiment. Suppose you are inside a train moving at a constant high speed. In the middle of the train, you hold a flashlight and shine a beam of light straight upward toward the ceiling. To you, inside the train, the light travels in a straight vertical line from the floor to the ceiling and back down again. It is a simple up and down motion. Now imagine a second observer standing on the railway platform, watching the train rush by. From this observer's point of view, the light does not travel straight up and down. Instead, because the train is moving forward, the light follows a diagonal path like the motion of a tossed ball inside a moving carriage. To the observer on the platform, the light travels a longer slanted path. But here is the crucial point. Both observers must measure the same speed of light. If the speed is the same, but the path is longer for the platform observer, then the time taken must also be longer. In other words, the clock inside the moving train must appear to tick more slowly. This is called time dilation. Time itself stretches depending on motion, and if time can stretch, then space must also adjust. Otherwise, the universe would contradict itself. Measurements of length also change depending on the observer's motion. Objects moving at high speed appear shorter in the direction of motion. This is called length contraction. These effects are not illusions or measurement errors. They are real features of the universe. Each observer measures space and time differently, yet the laws of physics remain consistent for all. So what does this mean? It means that space and time are not independent. They are woven together into a single four-dimensional fabric known as spacetime. To understand this, imagine you are describing an event, say, a firework exploding in the sky. To describe it fully, you must say where it happened and when it happened. The location alone is not enough. The time alone is not enough. Both are required. In Newton's world, these were separate descriptions. Three numbers for space, one number for time, but in the new picture, they are not separate at all. They are different aspects of the same thing, like length and width are aspects of a surface. This idea was expressed beautifully by the mathematician Hermann Minkowski, who once said, henceforth space by itself and time by itself are doomed to fade away into mere shadows, and only a kind of union of the two will preserve an independent reality. Space-time is this union. Imagine space-time as a vast, invisible fabric stretching across the universe. Every event, every heartbeat, every falling leaf, every exploding star is a point in this four-dimensional tapestry. Different observers, moving at different speeds, slice this fabric in different ways. What one observer calls space and time may not match another's description, but the deeper structure, the space-time itself, remains consistent. This is one of the most beautiful ideas in physics. Reality is not built from separate ingredients of space and time, but from their union. and from this union comes a new understanding of the universe. Distances and durations are no longer absolute, they are flexible, relative, shaped by motion and gravity. The universe becomes more dynamic, more subtle, and more interconnected than anyone had imagined. What once seemed like a rigid stage and a ticking clock are revealed to be threads of the same cosmic fabric woven together in the grand tapestry of spacetime. Time, to the human mind, feels like the most dependable thing in the universe. It marches forward with steady confidence. Seconds turn into minutes, minutes into hours, and hours into years. We grow older, seasons change, and the rhythm of time appears to be universal, an invisible river flowing at the same rate for everyone. But this comforting belief is, in truth, an illusion born from our slow-moving world. In the realm of very high speeds approaching the speed of light, time itself begins to behave in a most unexpected way. It stretches, it slows, it becomes flexible, like a piece of soft clay shaped by motion. This effect is known as time dilation, and it arises directly from the fundamental principle of relativity. The speed of light is the same for all observers. To understand this, let us return to a simple thought experiment. Imagine a perfectly mirrored box. Inside this box, a single particle of light, a photon, bounces between the floor and the ceiling. Each time it strikes the ceiling, the box records a tick. Each time it strikes the floor, it records a tock. Together, these bounces form a simple clock made of light. We call this a light clock. Now imagine you are sitting next to this clock in a spaceship floating quietly in space. To you, the photon travels straight up and down, bouncing between the mirrors. The distance is short and direct, and the clock ticks at a steady rhythm. But now suppose the spaceship begins to move at an enormous speed close to the speed of light past an observer who remains stationary outside. To the stationary observer, the light inside the clock no longer travels straight up and down. Because the spaceship is moving forward, the photon must trace a diagonal path, much like a bouncing ball inside a moving train. Instead of a simple vertical motion, the light now follows a longer, zigzag route. Here is the key idea. The speed of light must remain the same for both observers. The light cannot move faster just because the spaceship is in motion. Its speed is fixed by the laws of nature. But if the light travels a longer path at the same speed, then it must take more time to complete each tick of the clock. This means that to the stationary observer, the clock inside the moving spaceship ticks more slowly. Time itself appears to stretch inside the moving frame. This is the essence of time dilation. Mathematically, this effect is described by the equation equals 1 2 2t equals 1 c2 v2t. Here, t is the time measured by the stationary observer, t is the time experienced by the moving observer, v is the velocity of the moving object, c is the speed of light. As the velocity v approaches the speed of light, the denominator becomes smaller and the time experienced by the moving observer slows dramatically. At everyday speeds, cars, airplanes, even rockets, this effect is so tiny that we do not notice it. But at speeds close to that of light, the effect becomes profound. Let us imagine a dramatic example. Suppose a pair of twins are born on Earth. One twin stays on the planet, living a normal life. The other boards a spacecraft capable of traveling at nearly the speed of light. The traveling twin journeys across the galaxy and returns years later. To the twin on the spaceship, perhaps only 5 years have passed, but on Earth, decades may have gone by. The Earthbound twin is now much older. This is not science fiction. It is a real prediction of relativity known as the twin paradox, and experiments with high-speed particles and precise atomic clocks have confirmed it many times. Even today, satellites orbiting the Earth, such as those used in the GPS system, experience tiny amounts of time dilation. Their clocks run slightly differently from clocks on the ground, and engineers must correct for this effect. Otherwise, navigation systems would drift by kilometers each day. Time dilation is not just a theoretical curiosity. It is part of the functioning of our modern technological world. But beyond the equations and experiments lies a deeper philosophical lesson. Time is not the rigid, universal heartbeat we once believed it to be. It is personal, it is relative. Each observer carries their own clock, and those clocks do not always agree. In a sense, every moving object writes its own story of time. The faster it moves, the more slowly its story unfolds. This reveals something deeply poetic about the universe. Time is not an absolute master ruling over everything. It is a participant in the cosmic dance, shaped by motion, speed, and gravity. The universe, it seems, is not governed by a single ticking clock, but by countless clocks, each keeping its own rhythm, each telling its own tale of time. For centuries, the human mind placed mass and energy into two very different categories. Mass was the substance of the world, the solid, tangible stuff that made up stones, trees, planets, and people. Energy, on the other hand, was something more abstract: motion, heat, light, or electricity. It was what things had or did, not what they were. A rolling ball had kinetic energy, a hot stove had thermal energy, but the ball itself, the iron of the stove, the matter that made them, this was considered separate. Matter was matter, energy was energy. The two lived in different realms. This separation felt natural because in everyday life matter seems permanent. A piece of metal does not suddenly vanish into pure energy. A mountain does not dissolve into light. The world appears stable, solid, and enduring. But nature, when examined at its deepest level, often refuses to follow our intuitions. The story begins with the ideas of special relativity. Once it became clear that space and time were not absolute, and that the speed of light was the same for all observers, the laws of motion had to be rewritten. Energy and momentum, two central concepts of physics, had to be reconsidered under these new rules. In classical physics, the energy of an object in motion is given by a familiar formula: E equals 21 mv2. This equation tells us that energy depends on mass and speed, but it applies only at speeds much slower than the speed of light. As velocities approach light speed, this formula begins to fail. When the equations of relativity are applied, something remarkable appears. Even when an object is completely at rest, when its velocity 0 v equals 0, it still possesses energy. This is not energy of motion, nor of heat, nor of any obvious activity. It is energy simply because the object has mass. This insight leads to one of the most famous equations in all of science: E equals mc2. Here, E represents energy, m represents mass, c is the speed of light. At first glance, the equation seems almost too simple, but its meaning is profound. It tells us that mass itself is a form of energy. The speed of light, c, is an enormous number, about 300,000 kilometers per second. When we square it, the number becomes unimaginably large. This means that even a tiny amount of mass corresponds to an enormous amount of energy. To grasp this, imagine a small paperclip. It weighs only about 1 gram. If that entire gram of mass were converted into energy according to E equals mc2, the result would be equivalent to the energy released by a large explosive enough to power a city. For ours, this is not just theoretical, it is exactly what happens inside the cores of stars. Deep within the sun, hydrogen atoms collide and fuse together to form helium. When they do, a tiny fraction of their mass disappears. It does not vanish into nothingness, it transforms into energy. That energy travels outward as heat and light, eventually reaching Earth as the sunlight that warms our skin and nourishes all life. Every sunrise is a quiet demonstration of E equals mc2. The same principle is at work. In nuclear reactors and atomic bombs, in nuclear fission, heavy atoms like uranium split apart and a small portion of their mass becomes energy. In nuclear fusion, light atoms combine, again converting a small amount of mass into tremendous energy. In both cases, the energy released is far greater than that produced by chemical reactions like burning coal or gasoline. This is because chemical reactions rearrange electrons, while nuclear reactions tap into the very structure of the atomic nucleus, where mass and energy are deeply intertwined, but beyond its practical applications. The equation carries a deeper philosophical message. It tells us that the distinction between matter and energy is not fundamental. They are two faces of the same underlying reality. Matter is simply energy in a stable, condensed form. Energy is matter set free. A rock, a tree, a human body, all are composed of energy bound together in a particular arrangement. We are, quite literally, made of frozen light. This idea reshapes our understanding of the universe. It reveals a hidden unity behind the diversity of forms we see: the stars in the sky, the atoms in our bones, the light from a distant galaxy, all are expressions of the same cosmic substance, energy. And perhaps there is something quietly poetic in this realization. The warmth of the sun, the glow of a candle, the motion of the wind, and the matter of our own bodies are not separate things. They are different melodies played on the same instrument. The equation equals 2 is not merely a formula, it is a bridge between matter and light, between substance and motion, between what we see and what we feel. It tells us that the universe is more unified, more elegant, and more interconnected than we ever imagined. For thousands of years, gravity was one of the most familiar yet mysterious forces in nature. We feel it every day. It keeps our feet on the ground, pulls raindrops from the sky, and guides the motion of the moon around the earth. It is so common, so constant that we rarely question its deeper nature. In the 17th century, Isaac Newton gave humanity its first great explanation. He described gravity as a force of attraction between masses. According to his law, every object in the universe pulls on every other object. The earth pulls on the apple, the sun pulls on the planets, and the planets pull on each other. Newton's equation for gravity was elegant and powerful. It could predict the motion of planets with astonishing accuracy. For over 2 centuries, it stood as one of the greatest triumphs of human thought. But there was something unsettling about Newton's gravity. It acted at a distance instantly. If the sun were to suddenly vanish, Newton's theory implied that the Earth would feel the change in gravity immediately. There was no delay, no signal traveling through space. The effect was instantaneous. This idea troubled me deeply. It seemed to contradict the principle that nothing, not even information, could travel faster than light. If the speed of light was the ultimate limit in nature, how could gravity act instantly across vast cosmic distances? There had to be a deeper explanation. The answer emerged slowly through years of thought experiments and mathematical struggle. But the key insight came from a simple question: what does gravity feel like? Imagine you are inside a sealed elevator in deep space, far from any stars or planets. The elevator is floating freely. Inside, you feel weightless. If you release a ball, it simply hovers beside you. Now imagine that a powerful rocket engine attached to the elevator begins to accelerate upward. Suddenly, you feel a force pressing you against the floor. If you release the ball, it falls to the floor, just as it would on Earth. Inside the elevator, you cannot tell whether you are standing on a planet with gravity or simply being accelerated upward in empty space. The two situations are physically indistinguishable. This idea became known as the equivalence principle. It suggests that gravity and acceleration are, in a deep sense, the same thing. From this insight, a new picture of gravity began to take shape. If acceleration can mimic gravity, then perhaps gravity is not a force at all. Perhaps it is something more subtle, something built into the very structure of space and time. Remember that relativity had already shown that space and time are woven together into spacetime. Now imagine this spacetime as a flexible fabric rather than a rigid stage. When a massive object like a star or planet sits in spacetime, it does not simply exist there. It changes the shape of spacetime around it. It bends it, curves, it distorts it. To visualize this, imagine placing a heavy ball on a stretched rubber sheet. The sheet sags under the weight of the ball, creating a curved surface. Now roll a smaller ball across the sheet. Instead of moving in a straight line, it follows the curved path created by the heavy ball. From a distance, it might look as though the smaller ball is being pulled by an invisible force, but in reality, it is simply following the curved shape of the surface. This is how gravity works in general relativity. The Earth does not pull the moon with an invisible force. Instead, the Earth curves the spacetime around it. The moon simply follows the natural path through that curved spacetime. In mathematical form, this idea is expressed by the Einstein field equations: G plus G equals T. Though the symbols may look intimidating, their meaning is poetic. On one side of the equation is the geometry of spacetime, how it bends and curves. On the other side is the energy and matter within it. The equation says, in essence, matter tells spacetime how to curve, and curved spacetime tells matter how to move. This is the heart of general relativity, and its predictions have been confirmed in many remarkable ways. Light bends when it passes near massive objects, an effect first observed during a solar eclipse in 1919. Time itself runs more slowly near strong gravitational fields. Massive stars can collapse into black holes where spacetime curves so intensely that not even light can escape. Even the expansion of the universe and the ripples known as gravitational waves are consequences of this theory. But perhaps the most beautiful aspect of this idea is its simplicity. Gravity is no longer an invisible force. acting across empty space. It is the shape of space and time themselves. We live not on a rigid stage, but on a dynamic, flexible fabric that responds to the presence of matter and energy. Every planet, every star, every galaxy gently reshapes the geometry of the cosmos, and in this grand, silent dance of curvature and motion, the universe reveals itself to be far more elegant than we ever imagined.